Okay. All right. Okay. Alive, alive. Okay. Am I on? Okay, great. All right. Hello, everybody. Good morning. Happy equinox. Yeah. And this. Okay, this is Silicon Valley Fourth Interest Group, and I'm CH Ting. And this morning, my topic is not entirely fourth, third Vera coefficient. Okay, and let me see. So the summary, I'll talk a little bit about the gas, liquid, solid equilibrium, and then second and third Vera coefficients. Then I will review the work on the Vera coefficients, starting from Van der Waals and so on and so forth, up to Lee Kessler in 1975. And then, of course, that's my Vera equation, the cubic Vera equation. Okay, I'm very glad that Sam Chan's here. And I don't know if you remember this paper we wrote in 1972. At the time I was teaching in the Zhongzhen Institute of Technology, which is a military technology school in Taiwan. And there was a chemistry department then, and Sam was among one of the students. And because he was at the top of his class, after graduation, he was invited to be the assistant to the department. And he actually served as the department manager for a number of years. So in 1972, we wrote this paper, the gas, liquid, solid equilibrium, using a simple equation of state. And here, let me just remind you that we try to extend the Van der Waals equation of state. And what we did is to put a delta function-like term here, so that it gives a very sharp spike at the point where liquid probably will convert into solid. So this at the time we believe it is a good equation of state which is capable of describing the gaseous, liquid, and solid phases of a pure compound. And what led to this study was this Waals computer. In the 1970s, I think I was in Taiwan and missed all the excitement of the mini computer era. But the end of the wave actually reached Taiwan also. So one day Sam came to my office and said, "Hey, the physics department got a Waals computer, and it's like this, okay? I don't know if it is exactly the model, but as I remember, it has a wider cartridge. So it accepts a wider paper. And it actually can plot. It does printing okay? It has a ball. Yeah, a ball printer. And then it has a plotting mode, so that it just plot dots, okay? And it advance tenth of millimeter or tenth of an inch every time you finish one line, instead of the regular space, the characters. So this one can do plotting very well. And as I remember, it talk basic. So you can actually, I think it's standalone. You can just type in a basic program and get it to do a lot of things. So we are kind of excited and borrow it from the physics department and play with it. And we say, what can we do with that? Okay, I say, yeah, we can plot the van der Waals equation, and if I insert that term, and I can plot the three-phase equilibrium. So that was that paper, and this is actually one of the plots that we generated. So it's very nice, and you can see at the this is the volume, and this is the pressure, the PV plot. So at the very when the volume is big, the pressure is very low, and it increases. If it is an ideal gas, it's PV equal to RT. And if you have the van der Waals equation, and it has an attractive term, so that the pressure actually getting lower, and it has a repulsion term, and when it goes to very low, molecules tend to repel each other, and the pressure goes up. And if we insert this term here and pull this PV curve down and create another S-shaped, then it causes it to produce another phase. And when this one is very sharp, the phase change would be very narrow, and that's what where liquid becomes solid. Okay, so this was nice, but at the time we really don't have the computing capability to really investigate all the aspects of this equation. But we believe this explains the three-phase equilibrium. So, 2 years ago, I revisited this paper and see if I can do a better job, because now I have a much better plotting algorithm, and I have the PC to display all these things. So I change, instead of using the van der Waals equation, I use a regular Wheeler equation and add these terms, so that it will give a very sharp peak at the high density portion of the PV isotherm. And I did some studies with the argon, and so you have to raise this term to 26 power in order to create this very sharp S-shaped curve. And so here I can calculate the triple point and triple point pressure and the volume of the solid, liquid, and gas. Okay, so that was 2 years ago. But the problem with that equation was that I don't like the van der Waals equation, because it has a singular point at V equals to B. Okay, and this of course pushes the curve way up at the V equals to B, but it prevents you to do any experiment below B. And so a regular Wheeler equation with the second term and third term, the second term shows you the attractive force among molecules, and the third Wheeler term gives you the repulsive force. And this equation is quite adequate, and it doesn't have the singularity. And the actual singularity is at v equals 0, which is entirely reasonable because you cannot, the volume does not go negative, but it can go as close to 0 when you increase the pressure. So, but I look into the literature and found that the second Vieira coefficient is kind of okay, but the third Vieira coefficient that's required to study PV isotherm at a high pressure and a low volume does not agree with what's reported on the in the literature. So, in the for the argon, which I studied quite extensively, the second Vieira coefficient from high temperature, it decreases and to a negative value. And in all the literature about the third Vieira coefficient, they all seems to increase to the critical point, and then it drops down. Okay, and this is unreasonable. Okay, but that's what the experiment, most of the experiments showed. And in the 2 years ago when I did the study, I found that actually this is caused by their regression analysis. They only do the regression analysis for the gaseous phase, and it does not include the data in the liquid phase. If you include the data in the liquid phase, then this curve goes way up and doesn't never goes down. And that's the reasonable behavior, because the second term represented the attractive force among molecules, and the third Vieira term represented repulsive force, and the repulsive force would only increase and would only increase when the temperature gets lower. So this drop is totally unreasonable. So from most of the studies reported the value, you got this curve. And I insist that the correct curve is going to increase and not decreasing. So I was happy with that, but I thought I was the first one which found this discrepancy. And the couple a month ago, I started saying, well, can I find any prior study? We have been studying this for more than 100 years, okay? And are there any good experiment data on this second and third Vieira coefficients, which can substantiate my claim? Because the data I looked, one guy wrote actually 2 books on the Vieira coefficient, and he claimed that the shape was the second Vieira coefficient behaved that one. There's no question about this one. But in his 2 books, and up to now, most of the references to the third Vieira equation claim that third Vieira coefficient behaved that way. So, Vieira equation, which is a much general equation than Van der Waals equation. So it generally says that the best representation is not P as a function of V and T, but Z, which is called compressibility. And this compressibility is P over RT and times rho. Rho is molar density. Okay, so this term, the first term is 1, and that's the ideal gas. Okay, if this compound behaves like an ideal gas, the compressibility should be 1. Okay, and then if it is a real gas, then you have to consider further terms. And the second term is attraction. So B generally tends to be 0, tends to be less than 0, and C tend to be positive. So this gives the balance between the attractive force and the repulsive force. And then if you want to fit data more closely at high density, then you need to consider all these terms. So the Weir equation, if we show the relationship between compressibility and pressure and temperature, we can use this this equation, and this equation can be expanded indefinitely to fit experimental data. And remember that the dependence of rho is in a serial expansion, and all the coefficients, second Weir coefficient, third, fourth, fifth, and so forth, they are only temperature dependent. Okay, these coefficients are temperature dependent. Okay, so most of the studies with Weir equation, they kind of just push this equation, indefinitely, and the terms, the sum of the terms, they use 50 terms to represent the data, and they can get the data to fit quite nicely if you get enough terms. So let's look at the Van der Waals equation, which was proposed as early as 200 years, almost 200 years ago, 1873, and it has attractive term. A represent the attractive term, and B represent the repulsion. So this equation can be recast in Weir form. In this 1 over V minus B can be expanded in a Taylor series. Okay, and then the first term would be B over V, and then B squared over V squared, and B cubed over V cubed, and so forth. So this is the 1 over B can be expanded into a Taylor series, and then you have it in the Weir form. So the first term, of course, this is 1, corresponding to the ideal gas, and the second term, it has B minus A divided by RT. And this is quite nice because it shows that at very high temperature, when this is 0, you have a positive number. And then when temperature decreases, this term increases, and so it goes negative. So this is very nice. But the third Weir equation, third, fourth, and so forth, they are all constants. So from the Van der Waals equation, if you cast it in Weir form, the second Weir term seems to be correct, and the third term, we know it's temperature dependent, and this equation shows it's a constant, and that's why van der Waals is not adequate to describe the molecular behavior at low temperature and high pressure. So this is, I think, the basic reason why van der Waals equation of state is inadequate. So in 1929, BD, Richmond, and they proposed their equation of state. And this equation of state is very interesting in that, you know, the van der Waals equation has V minus B in the denominator. So if you approximate it with a VR equation, it actually becomes a V plus B. Okay, so this one avoid the singularity at V minus V equals to B, but he also recognized that the coefficients, the VR coefficients, are temperature dependent. Okay, so if we so the capitalized B and capitalized A, they are also both are temperature dependent and also depending upon the volume or the density. So he added the he will correct A by a lowercase a factor, and he will correct B with a lowercase b factor. If you combine everything together and rewrite the equation in terms of the inverse powers of V, then you get the VR equation. And the first term, the first term is 1. That's the ideal gas. The second VR equation, the second VR coefficient. In the van der Waals equation, you have these two terms. Okay, and it approximately give the right behavior, but the second VR coefficient decreases much faster than the first term of the 1 over t. So he added this 1 over t cube term to account for the rapid decreasing of the second VR coefficient. So this term does a very good job in accounting for the second VR coefficient. But lo and behold, the third VR coefficient is mostly negative. Okay, remember this negative sign. And when the t gets lower, this term gets very big, and the whole term becomes negative. And the third VR coefficient should not be negative. It should always be positive. So this term makes this Richmond equation of state inadequate at the lower temperature and high density, because the third VR term has a wrong sign. Okay. So this equation of state they have studied it. It cannot go down to below the critical point. Okay, the temperature has to be above a critical point. If it is above critical point, this equation works fine. But when it gets near critical point and below, it does not do a good job in representing the isotherms. And so in the 1940, Benedict came along, and he must have saw this deficiency. So he actually wrote out the second VR term is very similar to the Richmond equation, but the third term, he write out this one, but it doesn't work with that term. And he has to correct the third Vera coefficient with this very strange looking term with an exponential function in it. So because I came to the chemistry department library in Stanford and tried to look up this paper, and doesn't have it. Not that doesn't have it. I think they just display all the later literature, and I don't know. I didn't ask where they put the old literature. I think they store it somewhere else. So I couldn't find the original paper and couldn't really ascertain the reason why Benedict add this exponential term. And this exponential term is very troublesome because we wanted the Vera equation. We wanted the it all expanding in a series of row to row's power. Okay, and this term kind of throw everybody away, and it's very difficult to manipulate this equation with the exponential term. But when I look at this equation closely, I found that this term was added to correct this the third Vera coefficient. Okay, and another very interesting thing is that you notice that it has, of course, the zeros term, the ideal gas, and then the second Vera term to the row, and then third term row to the power of 2, row to the square, and then it skipped the row to the third and row to the fourth. It skipped 2 terms, and this is actually the third, fourth, fifth, and this is actually the 6th term. So there's a gap in this equation. So there are 2 terms missing. That means that the first 3 terms are fairly good, okay, and the deviation has to be in the row to the 5th term, and maybe on this depending on this exponential term. However, I have a great insight into this equation, and found that basically when you think about exponential function, it's it deviates, it diverges. You always think it is a diverging function, but since this the exponential is negative, so this is a convergent function. So it's a rapidly convergent function, and if you just expand this term, and if you take only two terms, it's a 1 and 1 to the x, okay, and this term multiplied with the this term, if we use 1 minus gamma rho square multiplied by 1 plus y plus gamma rho square, what happened? You got 1 minus this thing squared. Okay, so the result of this thing is just take this term and add to this third Vera equation, third Vera efficient. Okay, and then when this guy squared, it contributed to the 8th Vera coefficient. So it's way up there. And if we make this substitution and look at the Vera equation, you have the first term, second term, very nice, and the third term looks like this, and that's very nice. Okay, and then you skip 2 terms. You have the row to the 5th, and then the next one, which was resulted from the second term in the expansion, contributes to the 6th row to the 6th power, and that's the 8th Vera coefficient. So you know, you can pretty much ignore this high order Vera terms, and then the result is a cubic equation, and this behaves exactly as I expected. Okay, and this second Vera term, because of this the negativeness of this term, this will dominate when the t gets lower. So the second coefficient becomes very negative very fast when the temperature gets low, and this term is positive and make a third Vera coefficient rises very rapidly as the temperature goes low. This is exactly what I expected, and so I'm very happy with this. So here, this equation was proven to be very useful in industry, in the petroleum industry. So the Benedict actually studied all the lower light hydrocarbons, methane, ethane, and propane, butane, pentane, hexane, heptane, and octane. All these, he just listed all these coefficients, and it was used in the industry, in the petroleum industry, very extensively and very successfully. And the claim was that it can go to the twice the critical density and about 1/2 of the critical temperature. So it covers both the liquid phase and the gaseous phase very successfully. And I think a general error using this equation is about 2%, which is very good, at least. And then in 1972, Starling, this is a professor at Oklahoma University, and he tried to improve on the accuracy. And so he added more terms to the second coefficient, and added some more term to the third. And he kept the same exponential term. And if you expand that exponential term as I described before, and you get these terms. And these 2 terms, because he added more terms, it fits the data much more closely. And this equation claimed to be valid for 3 times the critical density and 1/3 of the critical temperature. So it covers a much wider range, and it claimed to be accurate to about 1%. So this was the this was the equation used by the petroleum industry ever since 1972, and so this one behaves at least up to this term behave just like what I've expected. So I think the experimental data, at least if we talk about Vera equations, this one probably gives the best results, and and it is very successful. And so in 1972, he published this book on about 15 different compounds, and he listed all the coefficients, and he actually used the equation to calculate not only the volume, he calculated other parameters of each and different compound. I think he's calculating Helmholtz free energy, entropy, and also fugacity, which is the free energy. So in this book, he published all these things. I try to recalculate all these using these equations and calculate both the second Weyl coefficient and the third Weyl coefficient, and see compare with what I calculated. And in 1975, Lee Kessler proposed even more ambitious project, in that he's tried to use a single equation to describe the behavior of all different compounds. And not only different compounds, they are also trying to calculate the physical property of mixtures. Okay, in the petroleum industry, they try to separate the distill the oil and fraction them into different fractions of different compounds. Yes.
Your row there, is that mass density or number density?
It's molar density. Molar density.
So it's a number density, number of molecules.
It's yeah, right. Yeah. It's basically pound, molar pound. Okay, so it's molar if the methane, which is the molecular weight is 16. So you have it's 16 pounds, the volume or the density of 16 pounds in a cubic feet. Okay. Mm-hmm.
Okay, I was just looking at it.
Yeah. This is density.
What's the bottom?
The molar density. Okay.
Right. Because the what's PV equals
and NRT.
NRT. What's that called?
The ideal gas law.
Ideal gas law. Right.
Yeah. So ideal gas law is generally if the R is picked for molar volume or molar density, and that allows you to compare different molecules of different molecular weight. Okay. Any other comment? Okay, let me finish with this one. So here, Lee Kessler, they proposed this equation, okay, and they are just use B1, B2, B3, B4 for the second Weyl equation, Weyl coefficient, and use C1, C2, and C3 for the third. And I think he must have recognized that this term contribute mostly to the third Weyl coefficient. So he actually named this coefficient C4. Okay, so this C4, if you do the same thing, you will move this one into here. But the problem is that he also, instead of a 1, he uses a beta. So if you have a 1 there, this thing expands, so you have only this a square of this term left. But if this beta is not as 1, you got something left for this term. So, but let me see if I have, and I don't think I have expanded out. Okay, so it's the same idea. Okay. And this is not adequate It has to be corrected. And they use this exponential to correct it. But I think they cheat. All these guys cheated. Try to scale people with this exponential term. And if you look at what they really meant was to correct the third Wheeler coefficient. And with that, I think it is also a little bit. This is a much more generalized equation, so that the temperature is not the actual absolute temperature, but the reduced temperature. Temperature is to be divided by Tc. And usually rho, you use a reduced density by divide this rho with the critical density. But in this equation, they try to correct for the compressibility, the difference between, because we know the compressibility, specifically at the critical temperature. The compressibility is a unique parameter for different compounds. So in order to include that particular property for a different compound, they correct the rho, not using their critical density, but use the critical pressure. And well, I think that's the what they want to achieve, because they want to account for the different critical point compressibility for different compounds. And if you include that, the equation is much more generalized. Okay, so it applies a single equation kind of applied to all different compounds. So that's very nice. But there are some details in it which I won't go through. But the only thing I want to point out is that this term, the main purpose of this term is to correct the third Wheeler coefficient. And using the Stirling equation of state, I calculate for all this. These are all the compounds listed in this book, and I try to calculate and recreate these second Wheeler coefficient and third Wheeler coefficient for all different compounds. And in the reduced form, okay, they are all corrected for the from the critical properties, and so all the different compounds ideally should behave identically, but they do not, and I think you can see that different compound has quite a wide spread of their values. And but the purpose of the Stirling enhanced equation of state is actually to predict the volume and the PVT behavior of light hydrocarbons, and they are extremely successful. But if you convert these plots into in the reduced form, you can see, there's a quite spread of the value, but the general trend are very clear that the B decreases as the temperature gets lower, and the C increases as temperature goes lower. But one problem I have for the last month, I was recalculating all these things and go back to the Stirling equation, to the Benedict equation. I didn't go back to the Richmond equation because I know Richmond equation doesn't work. So I'm trying to calculate all this from their equations plug in all the constants they published and try to recalculate the coefficients. One problem which is still bothering me is that this B and C second order. Oh, okay. Let me go down. I'm getting ahead of myself. So you see all these equations starting from the Benedict, they all point to that there is a gap. There's a big gap in the virial coefficient. So from the p-square term, rho square term, it jumped right to rho fifth. So and that means this the three terms dominates the virial equation. Okay, this thing is only contribute when the rho is very high, at very high density. Okay, and so it's at ordinary density. This term can be basically ignored. And if you ignore this, these terms, then what you have is a cubic virial equation with only three terms. And this three term probably accounts for all the PV behaviors to about 2% of accuracy. Okay, and this equation has all the nice properties of Van der Waals equation of state, but without a singular point. So Van der Waals equation, you have this term to represent the repulsive force when the V gets close to B. Okay, and this term C behave exactly like that, but without the limitation that V has to be greater than B. One interesting thing is that if you read the thermodynamic textbook, they always talk about the Van der Waals equation and show that with the Van der Waals equation you can solve it for the critical point and get a B and C, and also the critical compressibility. Okay. So this one, you can solve it. And then the B at the critical point, B equals to the negative of the critical density, of critical volume. Okay. And I'm sorry, this is squared, VC squared divided by 3. And the ZC, the compressibility, is 1/3. Okay. So this, if you use Van der Waals equation, the critical compressibility is 0.375. Okay, it is actually 3/8. So it is much better, but it's not good enough. Okay, because the real value is from 0.26 to 0.3. So there's some if you use this only three terms, this is a very glaring deficiency, but it's much better than the Van der Waals equation. And so I have another way of this equation can also be solved for the liquid and gaseous equilibrium, what I call the saturation region, where the gaseous phase coexists with liquid phase. So this equation, the cubic equation, can be solved exactly in closed form using the volume at certain pressure, the volume of liquid and volume of gas, and the pressure that state. Use these parameter, you can actually calculate second virial coefficient and third virial coefficient. And but the problem is that my calculation from this saturation property, the second virial coefficient agrees with what other people did, but the third virial coefficient is about a third smaller than the experimental values. So I'm still struggling with that problem, and that I don't know exactly what was wrong or what the problem is. But at the closer to the critical point, the agreement is quite good. Okay. So the virial equation was generally constructed with multi-property analysis or multivariable regression. So generally what they did, for example, these guys which use 30 or 50 virial terms. And what they did was just lay down this equation and then let the computer do the analysis. Feed the computer all the experimental data they have, and then let the computer grind out, do the regression analysis by itself, and then spit out the coefficient for you. 50 term. That's the largest. Not to the 50th, but each coefficient has temperature terms. So each temperature term has a coefficient, 50 terms, and they can be up to 8 or 9 virial coefficients. But each one has 4 or 5 temperature coefficients. Okay, so this is how they generally do it. But you should never trust a computer to do all these things. And you can if you give it enough variables, you can fit anything. Okay, yeah, right. Yes. Yeah. Mm-hmm.
I assume that there are people that are working on doing not the kinematics but the dynamics to find out what's behind stuff.
Yeah.
Because computers, you go, 50?
Yeah, no problem.
What can we do it now? We have computers.
Yes, exactly. So this is what I call the multivariable regression. Yeah, you have a virial equation, and you have a number of terms. Okay, you have a number of virial coefficients, and each coefficient has many temperature terms. Okay, so you just try to fit all these things into the use the equation and try to calculate the revalue. If it doesn't fit, you adjust any one of them, and the computer can adjust all of them simultaneously. Okay, if you write out everything into a set of linear equations, and you can solve the linear equations and to your heart's content. Okay, and this book called its multi-property analysis. So it not only calculates the volume, it also calculated the Helmholtz free energy, heat capacity, and sound of speed. Okay, all these things can be calculated. They actually derive some equations based on this, based on the virial equation. They can calculate all these properties, and they can compare all these properties, experimental probabilities, and then try to adjust the Veer coefficients, the terms, so that they can get a best overall fit. Okay, so that's what's going on. But you really don't know what's going on, and you really don't know what these coefficients or the constant mean.
How do they relate to reality?
It's the no, not reality. Okay, there's no reality here. In computer, there's no reality. Okay, it's all imaginary. Okay.
I'm saying if you do all these hundreds of terms,
Yes. Yeah. You really don't know what's going on, and then it depends how you write the regression. Okay, how you prioritize the data, which data you want to fit the first or the closest, and which you can ignore or you can tolerate more variance. So these don't trust them, okay? And they can get you a certain numbers, and they probably within the region that they fitted, you probably can get a good fit of the calculated value versus the experiment value. And now it looks like all the values, all the thermodynamic properties reported in the literature were calculated from these equations. And they are not, you just cannot get the original experimental data, okay? And they just try to fit everything and publish this equation, and then they publish the tables. And the tables are all generated by these equations. And the original data was kind of lost. Nobody knows.
They relate to real gas.
Right. So you know how these equations, how these coefficients relate to reality. Nobody knows. Okay.
That's what I'm saying. That's why you have to do the physics to find out why.
Yes. I think that's what my assertion here is. I think we have seen that the Veer equation has a big break. The fourth term and fifth term are all zero. So the first three terms is dominating. So when you do the analysis, you must try to fit this equation first. So get the first term is no question. It's a 1. Okay, that's ideal gas. Okay. Everything behaves that way when the temperature is high enough or pressure is low enough. But then when the pressure gets higher, the temperature gets lower, you have to worry about the second order. So fit this data and get the second order correct. And if the pressure gets even higher, temperature gets even lower, you have to consider the third Veer coefficient. You have to fit these two coefficients right, and then you worry about the rest. Okay, so I think the people should do it this way, not start with the whole bunch of equations and a whole bunch of data. You have to focus on the most important data, which is the second and third order coefficients. And if you do this right, and then you can worry about deviations or residues if they don't fit in the high temperature and low high pressure, low temperature region. Then you start worrying about the row to the fifth term, row to the sixth term, and so forth. Okay, here using my cubic Veer equation, second and third coefficient can be solved analytically in the saturation region. They should be used to check result from the second order regression. Okay, and the residues from the higher Veer coefficient must be analyzed after second and third order coefficients are determined precisely. Okay, but I don't think I have time or energy or money to do all this. This is my assertions. Properly determine the third Vieira coefficient will reduce complexity in the Vieira equation of state and improve its accuracy. My cubic Vieira equation of state has great value in improving our understanding of real gases, particularly in the saturation region. Okay, and I've seen reports. They tried, there are quantum mechanical bases for the second and third Vieira coefficients, and because we know the second Vieira coefficient is related to the interaction by molecular attraction.
Yes.
Okay, so there are people who assume Lennard-Jones attraction force between molecules, and they can actually calculate, compute the second Vieira equation using some very strange integrals. And the third Vieira coefficient is related to the three-particle interaction. Okay.
Now you're getting into the thing why statistical physics has to be used, because first you have, well, what's the interaction between two molecules of gas?
Yes.
Okay, now we've got that. Okay, what's now between three?
Uh-huh.
Okay, all right, now what happens is we get to 4, 5, and a whole large.
Yeah. And then it's reasonable to expect that the three-particle interaction causes the liquid to form. Okay,
yes.
Because of the third Vieira coefficient. And then when you have a solid, when it crystallized, how many molecules has to be interacting?
Yes.
1 against 12 neighbors.
Yes. Exactly.
Okay, so that's if you kind of think about it, it is up to the 12 Vieira coefficient.
Also take into account Bose-Einstein. Okay, now where you can now have all these molecules really close together.
Yeah.
And now you have to worry about their, if they have,
And
spin,
and for a single crystal, you have to consider all the molecules in the crystal, right?
Yes.
And so in my first the equation where I proposed to explain the solid, liquid, and gaseous equilibrium, you have to raise the V to the 26th power. Okay, so that in that sense, that's reasonable. Okay, so you have to consider the Vieira coefficient to the 26th or 27th Vieira coefficient to account for the existence of the solid phase. Yeah.
Compressibility was really important because in your equation you have pressure divided by that's the square of the sound speed. And when aircraft in World War II started going faster and faster, started closing in on that, all of a sudden the wings didn't start working. That's what they call compressibility.
Yeah. Okay, let me see. I think that's all my slides. Let me just scan to, questions? Or lunch?
Yay!
Okay, thank you very much. Okay, we'll go to lunch, and the afternoon session starts at 1:30, right?
I believe it's 1 today.
At 1, okay. So we'll see you 1 o'clock. Thank you.